Normal distributions are mathematical models of the distribution of data obtained for a variable. These models are among the most important used in statistics. In this video, I would like to show you several normal distributions so that you can see how they change as we vary the parameters for each distribution. To do this, I'm going to create plots using R statistical software. R is very good at creating plots, so I can use it to plot various models of normal distributions. The script that I'm going to use is not a beginner's script. Don't worry. If you're watching this to learn more about normal distributions rather than learning how to write more complex scripts, you're in the right place. Don't feel lost if you don't understand the functions that I'm using. My main purpose is to show you some plots. That said, I'll explain a bit about the functions that I used so that if you learn some more about R in this video, consider it a bonus. I start supposing that we are going to study a variable for which any score between 0 and 400 is possible. R has a function called seq, which is R shorthand for sequence. This is an easy way to create a sequence of scores. In this case, I've told the sequence function that I want scores from 0 to 400 in increments of 1. When I run this, I see in my environment window that I now have a new variable, s. That is indeed a sequence of scores, starting with 0 and continuing to, well, I can't really see that it goes all the way to 400 because after the 9 there are ellipses, but trust me, it does. The two parameters that define a normal distribution are the mean and standard deviation. I'm going to draw a normal distribution with a mean of 200 and a standard deviation of 50. I use the plot command to plot this distribution. I tell the plot command that I want my scores, remember they're in the variable called s, along the horizontal axis. On the vertical axis, I want to plot the density of a normal distribution. So I use dnorm, which is R shorthand for density of the normal distribution. I need to pause to answer your obvious question. What do we mean by density? Recall that when we graph actual data with a histogram, that the vertical axis is either the frequency, proportion, or percentage for the bars of our histogram. When we plot a model, such as a normal distribution, we want it to be available to model a variety of data sets with varying sample size. There is no set frequency for the vertical axis on our model. Instead, we call it density. Think about the term density if it is on the vertical dimension of our plot. This means that when we plot a curve higher in the vertical direction, there is a higher density of scores. That means there's more of them. This is related to frequency, except without having to specify a sample size. The type equals L argument simply tells R that I want to draw a line. The LDW argument tells R how thick my line should be. The bigger the number, the thicker the line. The ylim command says that I want my vertical axis to start at 0 and end at 0.008. How did I know to pick 0.008? Through trial and error. I tried creating this plot behind the scenes before showing it to you, and 0.008 was a good height for my graph to fit the plotting area but also use most of the vertical dimension. I then have my labels for the horizontal and vertical axis and my main title. Let's run it. So here is a model of a normal distribution in the range from 0 to 400 with a mean of 200 and a standard deviation of 50. If the standard deviation is 50, that means that looking 150 points above 200 and 150 points below 200 should give me a range that captures almost all my data. Recall that plus and minus 3 standard deviations should encompass almost all the data. Indeed, that is the case. Let's do it again, keeping the mean at 200, but changing the standard deviation to 60. I'm using the lines command instead of the plot command because this will superimpose a curve over the first one. If I use the plot command, my first graph will be erased and a new one will be created. I want to superimpose so that we can compare. I do add a COL command, which stands for color, so that I can make my new plot a different color than the first. I chose red. Here's the new normal distribution. It has the same mean and therefore the same center, but is not as high in the middle and is more spread out as we move towards the tails of the distribution. Why? Because it has higher variability. Remember that variability refers to the spread of scores. This distribution represents a set of data that is more spread out than in the first distribution. Let's keep it going and draw another normal distribution with a mean of 200 and a standard deviation of 70. This time I picked blue. The middle of the distribution drops down even further, and we see even more spread toward the distribution tails. More scores can be found further from the mean, indicating more variability. The standard deviation is 70, which is higher than both 50 and 60 of the two other normal distribution models. Let's get real wild and create one more with a standard deviation of 120. I'll make this one orange. There are quite a few more scores that are further away from 200 than in the first three distributions. In fact, this model doesn't even fit completely on this plot. Think about what 3 standard deviations would look like above the mean of 200 when the standard deviation is 120. That would take us all the way up to a score of 560, which is out beyond this plot, which only goes up to 400. Finally, let's go back to the original standard deviation of 50, represented by the normal distribution, that is black, but let's move the mean to 250. The result is this normal distribution model pictured in green. It has the same variability as our first normal distribution, but the center of the distribution has shifted to the right, up to 250. Here you see 5 normal distributions. 4 of them have the same mean, but different standard deviations. The 5th has a different mean. By altering the 2 normal distribution parameters, mean and standard deviation, or we can alter both, we end up with a different normal distribution. Which one should we use? That depends upon our context. It depends on what variables we are studying and what kind of data we obtain from these variables. Obviously, we want to choose models for our distribution that closely approximate what we actually see when we look at the distribution of data.